So today I'll first talk about, give a brief overview from last week, and then I'll talk about some basic PyTorch functions, try them out in Colab, and finally I'll cover two simple methods for forecasting, which is a direct method and also an iterative method. So for feature processing, when we have categorical features, we want to do this one-hot encoding. So basically we put a one at places where the object belongs to and zeros everywhere else. And for numerical features, want to normalize them so it roughly follow a standard distribution. So there are different ways where we can calculate the mean and standard deviation. And then given this raw data frame that we have on top, after we do all the data processing, we'll convert it to the second table here. And then for each time step, we'll just concatenate all the features into a long vector. So we end up with one vector for each time step. And the final array will have shape t plus tau, where t is the contact length and the tau is the length of the forecast horizon. And now let's talk about some basic PyTorch functions. So we can use those PyTorch functions to do the data processing that we covered. So the first one is a linear layer. So that will correspond to when all the when we're dealing with numerical variables. So in this case, if we have a linear layer that maps 30 to 10, that means 30 is number of input features. I want the output number of output features to be 10. In this case, the A here will be our weight matrix, and B will be the bias. So the weight matrix is defined given those two parameters that we input here. So in this case, it will be the transpose, which will be 10, 30, and the bias will have shape 10. So if we think about the example that we had from last week, given 30 steps, we want to predict 10 steps ahead. In this case, maybe our input X will have shape batch size times 30, and after this linear layer, our Y that's returned will have shape batch size times 10. So the other way to think about it is you only look at the last dimension of this input array, and it will change the last dimension. So the last dimension must match the first parameter for your linear layer or initialize the linear layer. And then it will map it to your second parameter that you put when you initialize the linear layer, which is 10. And the rest of the dimensions will be left untouched. Another type of layers that we'll need for data processing is this embedding layer. So this happens when we have categorical variables. In this case, it also has two parameters that we need to input. The first parameter will be the number of classes for this categorical variable. And the second dimension is still the output features, or the hidden dimension that will project the variable into. So here, for example, if x2 has shape batch size, and one thing to note here is that if we use this end or embedding, it will automatically encode the input tensor. So if you have batch size, if this shape is batch size, then after you call this embedding, it will first convert it to batch size times 5, because it will do the one-hot encoding for you and then apply the linear transformation. And once we are done with processing numerical features as well as the categorical features, we can concatenate the two vectors together. So from last slide, if the numerical features is batch size times 30 times 3, and the categorical features is batch size times 30 times 5, then after we concatenate them together, the output shape will be batch size times 30 times 8. So 30 is the number of time steps. And note that we put a dimension equals -1 here, so that it's by default it will be doing the concatenation along the last dimension here. So be along the 3 plus 5 equals 8. And then we can do a reshape. So we do batch size times batch size comma -1. And -1 here in reshape means that you'll ask PyTorch to automatically infer the size of the corresponding dimension. So in this case, because y3 from the last row here is batch size times 30 times 8, then after you call reshape, you already have the first dimension, which is still batch size. So you're left with 30 times 8. So that'll be 240 in this case. And then we can call it unsqueeze. So what unsqueeze does is we add a new dimension along a certain axis. So in this case, we put a new dimension on the first axis. So it become batch size times 1 times 240. And then if we want to get rid of all the dimensions with a single element, we can call this squeeze function, which will give us back the batch size times 240. And note that on the last slide here, when I call this unsqueeze, I need to assign it to a new variable y5. But if we don't want to do that and want still to just use the y4 as our variable, we can have this underscore here so that it does an in-place operation instead of having us need to reassign it to a new variable. And finally, we want to move it either to CPU or to GPUs. So in this case, we can just call y4.to, then torch.device. So CUDA means that we're using GPUs, and 0 means that which GPU we're using. And finally, we have this y4.detach. So detach means that when we're doing the forward propagation, by default, it will calculate all the, it will build the computation graph for the gradient calculation along the way. But if we call this y4.detach, it means we are actually removing the parent, all the parents from y4. So we don't involve its parents in the gradient calculation. And the other thing that's very important is activation functions. So note that if we simply have a bunch of linear layers and we take a composition of linear layers, we'll still end up with a linear layer. And we probably don't want that to happen. So we want to add some sort of nonlinearity along the way. So this is where the activation functions come into play. And one of the most popular activation functions is this ReLU function at the bottom left. So if you look at this figure, what it does is that it will cast all the negative parts to 0 and all the positive parts to be the identity function. So it keeps the positive parts as the same as before. And surprisingly, this kind of simple nonlinearity is actually enough to improve the expressiveness of neural networks. And I think there are actually some proofs that you can do to show that if you just have linear layer and a ReLU function, you can actually approximate any function that you want to approximate. And lastly, I will cover two basic methods for time series forecasting, which the first one is iterative method, and the second one is direct method. The direct method might be simpler to understand, so I'll talk about the right-hand side first. So on this figure, x will be the variables that are known for both the context and the forecast horizon. And u will be the observed inputs, and target variable will be the y here. So both the observed inputs and the target variables or the past targets are only available in the context. So you're only able to see it in those green boxes here. And your goal is to predict it for the forecast horizon, which will be this orange squares here. So what direct method do is that given those all those variables at the bottom, we will directly predict the entire forecast horizon at once. So we'll predict y hat t plus 1, y hat t plus 2, and y hat t plus 3 all at once. On the other hand, if we use the iterative method, then we only predict one time step at a time. So if our context, if in this case, in this figure, our context length is 3, and we still want to predict 3 time steps ahead, what we do is that after the third time step, we only predict y hat t plus 1, and then feed our prediction into the next time step to get a prediction for y hat t plus 2. And then do it again. So you feed your prediction for t plus 2 as input. And finally, you'll make the prediction for y hat t plus 3. So you'll iteratively make those predictions or recursively make those predictions. So the benefits of this direct method over this iterative method is that if you have a very long forecast horizon and if you iteratively make predictions, you can imagine that your error will accumulate along the way. Because when you make the prediction for y hat t plus 3, your input y hat t plus 2 is something that you predict from the last time step. And that might already have some error inside it. And if you do your prediction for next time step based on this error, then your error is going to accumulate and get larger over time. But for very short forecast horizons, the iterative method actually work quite well because we don't have the error accumulation issue. And we can also generate this iterative method to allow it to predict an arbitrary number of time steps. So for example, during training, maybe you only train it to predict time steps ahead. But during inference, we can apply it maybe 30 times. So we predict 30 steps ahead instead of just time steps. Okay, now let's go into more details on the iterative method. So a good example of an iterative method will be recurrent neural networks or LSTMs. So for those iterative methods, you'll always have some kind of memory vector, and you'll also have a feature vector. So the memory vector is what your model want to summarize from all the previous time steps. Since the only other thing that your model can see is the feature vector from this current time step. So everything from before time step t, you need to summarize into this memory vector. So a simple implementation would just be concatenating the memory vector together with this feature vector and feeding into multiple linear layers. So this MLP here. And then you'll predict two things. First, you'll update the memory vector. So because you still want to use the memory vector and pass it on to the next time step. And the other thing is to make a prediction for target variables. So for your feature vector at time step t+1, your target variables were missing originally, and you want to fill those target variables that are missing with your predictions. And then on the right-hand side, you'll start with a memory vector. You can either, a simple way to initialize memory vector is just to set it to be all zeros. So iteratively pass it into the model. So the A here will just be this linear layer or multiple linear layers. So the top arrows, the arrows that are pointing to the top, are the predictions that you make for target variables. And the arrows that are pointing to the right are the updated memory vectors. Do we have any questions so far? Okay. Now let's move on to an example to see how the stuff we covered actually works in terms of code. So for the first few meetings, we will be fine by just using Colab because we're not doing very heavy coding. And in 2 weeks from now, I think I will cover GitHub and also cover how to set up the server. So at that point, if you want to try more advanced models, which will take more time to do the training, then you probably cannot use Colab anymore because that's a limited compute time. And I will teach you how to set up the server. So we'll just be sticking with the Colab for now. And the first thing we do is to change the hardware from CPU to GPU. So the way to do that is click on the runtime here, click on change runtime type, and change it to GPU. And once you do that, run this block, it shall show that GPU is found. And the other thing that you might want to do is to connect the Colab to your Google Drive so you can save all your files. And so after your Colab disconnects, maybe you can still have the model checkpoints and everything. Yeah, this block takes a little bit of time to run every time. So once you do that, you can see where you're at. And the next time, if you save the file right here, the next time you connect your Colab to Google Drive, you should still be able to see the save files under the same directory. And next thing we are going to do is we are going to create a very simple data frame that we use as an example from meeting 1. So we'll have a total of 5 different instances, each of 1,000 time steps. And at every step, there will be 3 numerical features. One of them will be the target variable. And we also have 1 time covariate, as well as 2 numerical features. And the first numerical feature will have 4 classes, and the second numerical feature will just be our instance ID, which will be the same as the number of instances that we have, which is 5. And yeah, For simplicity, I just filled it all with random numbers. We'll end up getting this data frame right here. So each instance will have 1,000 time steps, and we have a total of 5 instances. So we'll end up having 5,000 rows. The first thing we want to do is to normalize the numerical features as well as prepare the categorical features. And for simplicity, I only do it for one instance. And as a homework, you can probably try to modify the code so that it can handle all the instances in parallel. So here I just selected the instance 1, and we only look at the numerical features. And to calculate the mean and standard deviation, we should only use the numerical features from the train split. So know that I might have this data frame day less than 700. And then we do this normalization. And for categorical features, we actually don't need to do anything at the moment. And our task here is still given 30 steps, and we want to predict 10 steps ahead. So if we, in the future, you'll probably need to write a dataset class along with the data loader class. So all this right here will go into the, everything above this line should go into the dataset class. And then once you have the dataset class, and you also putting all the parameters and initialize this data loader, this window selection or which instance, which windows you're picking for a current batch will be handled by this data loader. So right now, for the sake of illustration, I'm just gonna manually hard code it and do the numpy.stack to collect all those batch size number of windows. So end up with this batch size of numerical features and a batch size of categorical features. So we have 4 numerical features along with 2 categorical features. And at this point, we are ready to put those categorical features and numerical features into a neural network. So we will be using this linear layer to process the numerical features. And for each categorical feature, we should use a separate and/or embedding layer. The reason is that for each categorical feature, the number of input class will be different. So we must have a separate embedding layer for each categorical feature. And in this case, because we are using GPU, we should move both the linear layer along with the embedding layers onto GPU. And we should also convert it to PyTorch tensors. And notice that for the categorical feature, I also call this .long here, because for the and/or embedding layers, it will actually expect an integer instead of a floating number. So you'll want to cast it to an integer. For all numerical features, you can feed into the linear layer. And so the input size will be 32 times 30 times 4. And because here we define the D model to be 32. After we call this linear layer, the output will be 32 times 30 times 32. So we'll change the last dimension 4 to 32 based on what we defined here. For each of the categorical features, we'll first look at the first categorical feature. So here I'm just retrieving there's another thing I forgot to mention. So we can define this module list here, just the same as a list in Python. So you can just use this index to retrieve or to reference the first embedding layer. So the input shape will be 32 times 30. And after you call this embedding layer, you'll change the embeddings. You'll first do the one-hot encoding and then cast it into the 32 times 30 times 10. So add this extra dimension here. And this is defined back here, which specifies the number of output features. And then alternative is to process all the categorical variables all together. So you can have this for loop, which will loop through all the categorical features, and you'll call this concatenation function along the last dimension. So once you do that, your output embedding for all your categorical features will have this shape. And finally, you can concatenate your numerical features and the categorical features. You concatenate your embeddings together to get this final process inputs. And then I will show a quick example. Actually, I should be running all those blocks. I will show a quick example of an activation function. So for process inputs, if we have something like this, and we use this ReLU function. So ReLU removes everything that's below 0. So once we call ReLU on this tensor, you see that all the negative entries will be casted to 0. And there's another activation function that I can use, which does the same thing. So it does some nonlinear transform to the input tensor. So you can put everything that we have from before into a network class. So in the init, you should define your linear layer and also the embedding layers. In the forward, you do this, you feed your actual tensors into the linear layer and the embedding layers. So once I have it defined, I can initialize it. And we see that the shape of the return tensor is same as what we had from before. And finally, I will show the two simple methods to do the forecasting. So first step is same as before. So for every time step, we'll have a linear layer to map all the numerical features to a vector of length D model. So D model means the hidden dimension of the model. For each of the categorical variable, we'll use the embedding layer to map to the corresponding batch size. Once we do that, then for each time step, we can concatenate all the embeddings together into a long vector. And this will have shape D model, which comes from the numerical features, plus the sum of all the categorical variables. And this part, it can actually run in parallel. by just calling this n.linear. So process all the 30 time steps in parallel. I think we have already done this from the last part. So if we look at if we look at here, the time step, which is the second dimension here, once you call this n.linear, it actually performs operations for the entire 30 steps. And last step is this is just for simplicity. So I just flatten the entire embedding vector across all the context lengths and then feed into one single linear layer to get a prediction for each time step in the forecast horizon. So you'll expect the output shape to be batch size times the length of the forecast horizon, predict length, and the number of target variables. So still have this. This is actually something new from before. This is to prepare the ground truth so you can do training for this network. So prepare the batch of ground truths, which will correspond to the each of the windows that you have. And here, it's very much the same thing. So the first two rows are just doing the data processing. So convert all your numerical features and all your categorical features, you concatenate them, and then you feed into this second linear layer 2. And then finally, you want to flatten out, or you can just call this reshape function, and you'll go to this demodel times your contact length, and then you want to make the prediction all at once. So after this second linear layer, you'll have batch size times 30 times 32. And then we call this reshape, which happens here, reshape batch size -1. So flatten out the last two dimensions. So it'll be 30 times 32, which is 960. So this is the entire input vector into the final prediction head. And then after the last layer, you'll make your predictions. So in this case, we want to predict time steps. So we'll have shape 32 times 10. And you also want to do an unsqueeze, or you can do a reshape to match it to the number of target variables that you have, which is 1 in this case. So using this prediction, which we get from this network, we can define a loss function, which will be the mean square error here. So feed our predictions along with the ground truth tensor that we define here. Based on those two, we'll calculate a loss. So loss will be a single number. And we can define an optimizer. So this is what we covered from the last meeting. And based on this loss, we can call backward. And once we call backwards, you can actually check to see the gradient for each of the weights. So if we look at one of the linear layers, we see that its gradient has this shape. And we can actually examine its weights by calling dot weight. So it has a bunch of numbers here. And then we also print out its gradient. After we call this optimizer.step, we see that its weights actually get changed. So if we look at the first entry, it goes from 0.0 0.3124 to 0.3114. So we are actually updating the weights of the network. And then finally, we call it zero gradient. And if we call it zero gradient, I think it should return all zeros. Okay, and the last part will be this iterative method. So output shape will still be the same. So we have, actually it will be a bit different, depends on how we look at it. So the last, from the direct method, it will be batch size times 10 times number of target variables. But for here, because we're making the predictions for every time step, so it'll actually be batch size times 1, which will be the time step, and then number of target variables. And we do a for loop. So at every step, we get our prediction and then feed it back into the network to get the prediction for next time step. Okay, and this might seem a little bit long, but a bunch of it is actually the same from the direct method. So I guess I will just highlight where the differences are. So if we go back to the slide here, we see that at every step, we want to predict two things instead of just one thing. So in the direct method, we're just predicting this target variables here. But in the iterative method, we want to update our memory vector. So this is what's going on right here. So you not only want to predict your target variables, you also want to update your memory vector. So here, Earth is only for data preprocessing. So we still process all numerical features, also categorical features, concatenate them together. And in the first part, in the context lens, because we already have the, so if we go back to this slide or the slide before, so before this point, we still have the ground truth for target variables. So we don't need to feed the prediction from last time step into the next time step. We can just directly use the ground truth. So here, that's what we are doing. So the only thing that we care about is this memory vector here. We want this memory vector to summarize all the information from the context. And then we can get our first prediction. And once we have that, we can feed we can fill in this missing piece with our prediction and then feed it back into the model to get a prediction for the next step. And this is what's going on here, where you fill in the missing part with your predictions. And the other thing to be careful about is that you should call this dot detach when you pass your predictions into a next time step. So when you pass your, okay, I guess I don't have it on this slide, but oh, it's actually here. So if you pass your predictions from last time step into a next step, then you want to not calculate the gradient from the previous time step, and you only want to calculate the gradient from the current time step. And then finally, after you go through your entire forecast horizon, you'll get all your predictions saved here. And this will be your model predictions for entire forecast horizon. And those are also the same as before, except that we also need to define this. So recall that before for direct method, we only use all the variables from the context range. But there can also be some variables that are also known in the forecast horizon. For example, the day of the week or hour of the day. So for those information, we can put them as separate sensors. So that's what we're doing here. And then we don't want to feed the target variable into the model. So we mask it out with all negative ones. And finally, we get our predictions. So if you run this whole block, you see that our prediction will be the same as before, or its shape will be the same as before. And we calculate the loss, and we can still do this, use our optimizer, or you should probably define a new optimizer based on this iterative network. And then once you do that, you can update the weights. Okay, and this is all I have from today. So for next week, we'll talk about a more concrete example of an LSTM network. And I think we'll also talk about GitHub if time allows.